Hi guys, welcome to Amateur Chemistry. So, plastic bottles. If you think about it, they are kind of everywhere, since nowadays having a drink of almost any kind involves the use of one. Now, the average person just throws used plastic bottles into the trash, not thinking much about them, and honestly, that's exactly what I did until very recently. You see, having more time to think about the chemistry around us because of this amazing channel, I progressively became more and more fascinated with how this seemingly simple plastic bottle is actually a treasure trove of useful chemicals. The plastic most bottles are made of is something called polyethylene terephthalate, or PET for short, and apart from giving me one more reason to pet my cat, this name tells me the exact juicy chemical composition of this plastic. It's made of long chains of this thing here, called a monomer, and the plastic polymer it forms contains a bunch of these seemingly random hexagons. Now, they may seem that way to you, however, when I first saw them, my chemist neurons activated, since this is literally the structure of this little goober called benzene. Benzene has a special place in the heart of every chemist, be it for its rich history, the thousands of things it can be used for, or its quite potent carcinogenicity, and I think that every chemist agrees that it's good to have it in the lab. I always wanted to have some, however, because of it being literal cancer juice, many countries, especially in the EU, don't really like it. They actually kind of hate it in fact, and to this day I haven't been able to find affordable benzene anywhere. This brings me back to the structure of PET, which contains a really big amount of these benzene rings, and one day I had this wild idea of somehow tearing them out and turning them into homemade benzene. I hope that I painted you a good picture of why this would be kind of revolutionary for me and would also make a hell of a good project for the channel, since this is literally recycling on steroids. That's why a while ago, not really knowing what I am getting into, I set off on a journey to turn plastic waste into one of the coolest molecules, and since not many people seem to have attempted this before, I wanted to see if it could make some decent benzene. Anyway, before figuring out how I am going to forcefully tear through some plastic to steal its benzene, I first have to get some of it. This was quite easy, since after only like 2 weeks of saving every bottle I drank from, I collected 20 of them. They make for some good bowling pins and should contain around 400 grams of plastic, which is the scale I want to work on. I figured that even if my yield is trash, this much plastic should be enough to get a good amount of benzene, and before doing any chemistry, I had to prepare it a little. By prepare, I mean remove these annoying European Union caps, which are made of a different plastic, as well as compact the bottles a bit, since they currently take up way too much space. I want to grind them down as close to a powder as possible, and to start, I whipped out this comically large knife with the pointy part broken off for some reason. It made for a great tool in removing the tougher top and bottom parts of the bottles, leaving behind just the thin shells. To pulverize this mound of decapitated bottle corpses, I wanted to use a blender, however the plastic turned out to be weirdly hard to grind. It's kind of soft and brittle at the same time, and the blender just wasn't having it. I mean, I even tried blending it underwater, which gave no good results. I could spend hours developing some advanced plastic grinder and tear through the bottles in no time, but being the patient person wannabe I am, I turned to using these puny office scissors and some elbow grease. It took me like 3 hours, but I managed to turn all 20 bottles into these label-less clippings, perfect to be used in some chemical reactions. They only weighed 200 grams however, so to squeeze more plastic out of the bottles, I also processed their tougher parts. As expected, this was a big pain, and the only tool capable of splitting them was this massive tree pruner. It allowed me to finally reach my target 400 grams of cut PET plastic, and I also had to use a few of these darker colored bottles, since the 20 I started with weren't quite enough. Anyway, with this very hard-earned box of laboratory-grade plastic ready, I could now finally extract the benzene from it. There is unfortunately no single chemical reaction that just magically does that, and the best approach to take here is to slowly weaken the plastic. This basically means breaking progressively stronger bonds in its structure, and the best bond to start with is this one. It's something called an ester bond, and it's also the reason why this plastic is often called polyester. Breaking it would make the polymer structure completely fall apart and quote-unquote deshield the benzene. The resulting benzene-containing compound will then have a much easier time turning into pure benzene, which is exactly what I want. Breaking the ester bonds of PET isn't easy, and to do it reasonably quickly, I have to use some really angry chemicals. The one I am going to use is something called sodium hydroxide. It's often used for things like drain opening, and it's corrosive enough to eat through polyester reasonably quickly. To do that, however, it needs really high temperatures, which means that I can't really use water as the solvent for this reaction. I also can't do this reaction without any solvent, since heating the plastic too strongly would just burn it, and this means that I have to find something that's accessible and has a high boiling point. Fortunately, one such thing can be found in this car antifreeze I recently picked up, and it's something called ethylene glycol. It has a boiling point of almost 200 degrees Celsius and won't interfere with the reaction, making it the perfect thing to use here. Now, it can be readily bought in its pure form, however, I decided to extract it from antifreeze since I bought it just for this project. The glycol in it is mixed with various additives and a bunch of water, which I can luckily separate out quite easily by distillation. To start, I poured about half the antifreeze into a flask and then assembled it into a distillation apparatus. After turning on heating and stirring, everything quickly started boiling and a bunch of water began making its way into the receiving flask. I ended up with quite a bit of it, and when most boiled off, I quickly dumped the remaining antifreeze into the boiling flask. This will make me have to do only a single distillation to process it all, which is quite nice. Anyway, at some point there was no more water coming over, and the temperature of the vapor started rising, so I switched the receiving flask for a new one and began collecting my precious ethylene glycol. As the distillation went on, the antifreeze magically turned colorless, which I thought was weird. Anyway, in the end, I ended up with nearly a full flask of ethylene glycol, along with this antifreeze sludge, which smelled quite dreadful. To store my product, I got it all into this old jar, and it turned out that I managed to get 446 grams. Considering the full liter of antifreeze I started with, this was honestly quite mid. Nonetheless, it should be enough, and I seldom have distillations go this smoothly. With the glycol ready, I now have to come up with the setup for making the benzene, and this is where things get rather tricky. You see, a concentrated solution of sodium hydroxide at nearly 200 degrees Celsius is, let's just say, dangerous, and it can eat through things like flesh and glassware in no time. This means that I have to use a metal reaction vessel, and luckily I have a few of these steel paint cans, which should be just perfect. I chose a smaller one so that you guys will have an easier time seeing what's going on inside, and to start the reaction I loaded it up with half my ethylene glycol and 100 grams of sodium hydroxide. The reason why I am using only half my glycol is that I want to do this reaction in 2 batches, mainly because it should be easier to control. That's also why I didn't initially add any plastic and first want to dissolve the sodium hydroxide in the glycol. For that, I must heat this forbidden antifreeze, and the only heat source hot and at the same time gentle enough to work for this is my trusty electric stove. If you are a long-time viewer, you probably know that it went through a lot, and with all its legs missing, I had to use this old pan for support. It should also nicely contain any potential spills, and with this high-tech setup ready, I got my can onto it and could now finally start the reaction. What's quite interesting is that before I even turned on the stove, the dissolving sodium hydroxide started warming up by itself and turned yellow, which wasn't really a good sign. I threw in some plastic just to see if the heat from the sodium hydroxide could start decomposing it, and indeed after a few minutes it became opaque. This meant that this whole thing is working, and to speed everything up I cranked the heating. After a while, all the liquid inside the can got much less viscous and turned from brown back to yellow, which I guess was good, and with all the sodium hydroxide in solution, I could now freely start adding half my plastic shavings. I covered the can with a lid so that it could get even hotter, and then, being the genius I am, I left the lab to grab a snack. Upon coming back, I nearly had a heart attack since the can apparently decided to turn into an active volcano. It turned out that it got so hot that the glycol started boiling, which resulted in pretty much the whole reaction mixture being sprayed around everywhere. The pan didn't really do much to stop this corrosive wax from pouring all over my fume hood, and cleaning this whole thing was one of the most tedious things I've ever done. Fortunately, after like 4 hours, I managed to get everything operational again, including the stove, which suffered some serious injuries. For the second and hopefully successful run, I decided to use one of the bigger paint cans, which should contain the corrosive solution much better. I also caved in and ordered some commercial ethylene glycol since I had only half of mine left. Likewise, to make up for the sizable amount of plastic now missing from the initial 200 grams, I got a few new water bottles and tortured my fingers some more. Anyway, with all the reagents resupplied and the setup fixed, I was now ready to run this reaction one more time. I began by weighing out the ingredients, and this time I wanted to have some more solvent around, so I used the roughly 220 grams of my remaining ethylene glycol along with nearly the same amount of the commercial stuff. This should make the solution less boiling prone, and as the second ingredient I again used 100 grams of sodium hydroxide. I got the resulting mixture onto my stove and this time started heating it right away. When it got to temperature, I started sprinkling in the plastic, and this time there were fortunately no signs of boiling. Nonetheless, I watched the reaction closely for its whole duration, as if that tames it somehow, and now that I got this process working, I can finally talk about what's going on here. This reaction is called base hydrolysis, and it cleaves the ester bonds of the PET plastic, producing something called sodium terephthalate and ethylene glycol. Sodium terephthalate is the thing I want to later turn into benzene, and the created ethylene glycol nicely replenishes any that might have evaporated away. Under such severe heating and an excess of sodium hydroxide, this reaction proceeds quite quickly, and you can actually see that as the whitening and eventual crumbling of the plastic chunks, which turn into this white sludge. Anyway, under my watchful eye, this reaction seemed to go much better than before, and it was not long before I added in all the plastic and most of it dissolved. I then took this forbidden recycling soup off the stove and allowed it to cool down. Now, to proceed in making benzene, I have to somehow rip those two groups of the sodium terephthalate, and this is where things get quite interesting. You see, the bonds that stick them to the benzene ring are way stronger than the ones I broke earlier, and it's usually very hard to destroy them. Fortunately for me, in this specific situation I can do that with relative ease, and all I need to do is chemically beat up the sodium terephthalate. This basically involves using a strong base, and since sodium hydroxide is a strong base, it's the only thing needed for this reaction, which makes it weirdly similar to the previous one. What's different about it, however, is that heating the hydroxide to 200 degrees Celsius won't work, and it basically has to be molten. You can imagine just how corrosive and dangerous that is, and since sodium hydroxide melts at a whopping 323 degrees Celsius, I won't even be able to use my electric stove. This also creates another problem, since at such high temperatures the sodium terephthalate would just decompose instead of becoming benzene, which is not cool. Fortunately, after some research, I found that you can have molten hydroxide at much lower temperatures, and what makes it possible is this little goober right here called potassium hydroxide. Now, it is an even stronger and more corrosive base than sodium hydroxide. It also has an even higher melting point, which honestly doesn't make it seem that useful. When mixed with sodium hydroxide in the right ratio, however, the two create something called a eutectic mixture, which, while retaining all their corrosiveness, melts at only 170 degrees Celsius. This is kind of huge for me, as it would both make the reaction much easier and potentially higher yielding, and I was really eager to try it out. For that, I added 25 more grams of sodium hydroxide into the can, followed by 55 grams of potassium hydroxide, which should result in a slight molar excess of the eutectic mixture. I stirred everything up using my trusty fork and equipped the can with this cool modified lid which I made in the previous video, and it will make it compatible with all my glassware. I now wanted to assemble this thing into a distillation apparatus, however at the last moment I decided to split the mixture between two cans and do the reaction in two batches just in case something goes wrong. When that was done, I assembled one of the cans into a distillation setup on steroids featuring this old gas camping stove. It's stupendously powerful for its size and should be the perfect thing to provide all the heat necessary for the reaction, and I have to cover a part of it with a wet cloth to prevent it from melting itself. Anyway, to begin the reaction, I set the stove to low heat and waited for some vapors to appear. The first thing that should come over is ethylene glycol, which I chose to leave in the can since it will allow everything to fairly mix. Now, the reaction that's going on here is rather simple. It's known as alkaline decarboxylation, and through the chemical brutality of molten hydroxide, it turns the sodium terephthalate into benzene and some sodium and potassium carbonate. Now, even at modest temperatures and using the hydroxide eutectic, this reaction generates a ton of byproducts and tar, which I will later have to remove from my benzene. Overall, when done in a metal vessel, this reaction should be pretty tame, however, just as I was about to leave for a snack again, this happened. Out of nowhere, a ton of this white foam started making its way up the can, and before I cut the heat, some of it nearly escaped to the condenser. This was quite weird since the glycol didn't seem to foam before at all, and now every time I tried to restart the stove, the foam appeared again. I was honestly dumbfounded and didn't quite know what to do, however, I really didn't want to give up on this project. As a kind of last resort move to try taming the foam, I got rid of the aluminum foil I originally insulated the can with and again turned on the stove, this time cranking it all the way. It somehow worked, and even with everything vigorously boiling, no foam seemed to appear. This whole thing seemed quite weird, however, I decided to simply not think about it and just move on, since now the reaction seemed to be picking up. At first, mostly just the glycol came over as this yellow liquid. There was also a bunch of some awfully smelling cancer gas, which made this whole thing even more dangerous than it already was. I luckily did all this in a very good fume hood, and after a few minutes of intense heating, some brown oil started making its way into the receiving flask. This had to be benzene, and I was honestly amazed that I actually managed to make it. There seemed to be quite a bit of it, and at some point I decided that the reaction mixture was dry enough to again insulate the can with aluminum foil, which will make the heating more even. This time, the foam fortunately didn't show up, and I continued the distillation until no more vapors escaped from the can. After turning off the stove, I disassembled the apparatus, and apart from a white sodium and potassium carbonate brick in the can, I was left with this small layer of benzene floating on a bunch of ethylene glycol. It didn't seem like too much, however, I still have a ton of material to process, and I first wanted to take care of the second half of the hydrolysis mixture. Distilling it went much smoother than before, with no awful foam being present and a bunch of benzene coming over. Together, these distillations left me with a flask containing a pretty decent amount of benzene, and before purifying it, I repeated the whole process again to take care of all the plastic I still had laying around. With so much new wisdom and smaller urges to go for a snack, it wasn't as painful as before, and after only half a day of work, I had a second benzene-containing flask ready. It seemed to have even more product than the first one, and now with the essence of like 30 plastic bottles condensed into these two flasks, it was time to purify the benzene from it. For that, I have to separate it from the copious amount of ethylene glycol it's mixed with, and I theoretically could just pour it off. However, benzene dissolves in ethylene glycol to some extent, and I wouldn't really be happy with losing a bunch of my product. Because of that, I decided that I will just distill the benzene out, which should nicely separate it from most other contaminants. For that, I poured the contents of both flasks into a bigger one and assembled it into a fractional distillation setup. This beast of an apparatus will allow me to separate out the benzene much better than a regular distillation apparatus would, and it's all made possible through this long glass tower here called a fractionating column. You see, upon heating the benzene-containing flask, a bunch of junk boils along with the benzene, and if I were to just directly condense those vapors, my product would be really dirty. By traveling up the column, the vapors condense and boil hundreds of times, separating way better. Using a thermometer probe, I can easily figure out what I am currently collecting, and it didn't take long for the surprisingly pretty benzene vapors to reach the condenser. The liquid that began collecting in the receiving flask was quite cloudy and came over below the expected 80 degrees Celsius, however, this is actually benzene. You see, benzene being a very oily liquid normally doesn't mix with water, however, if a mixture of the two is heated together, its vapors contain both benzene and water and come over at a lower temperature than they normally would. This is called an azeotrope, and for benzene and water it boils at around 69 degrees Celsius and contains 29.5% water. This basically means that I will later have to chemically remove it from my benzene, and the most important thing here is that the benzene I collect is quite pure. Anyway, when the receiving flask was almost full, I replaced it with a bigger one, and since the temperature of the vapors started rising, I should now begin to collect some drier, purer benzene. At first, it was exactly what happened, however, after a while some weirdly yellow liquid started coming over with my benzene. This is basically another installment of the curse of yellow, which I always seem to suffer when distilling things, and it means that there is some volatile impurity mixed in with the benzene. For now, however, I figured that I shouldn't care and continued the distillation, changing the flask one more time. When the temperature started spiking, I turned off the heating and took apart the apparatus. This left me with these 3 flasks containing colored fractions of what was meant to be a nice colorless liquid, and since I want my benzene to be high quality, I decided to purify them all. For that, I whipped out this piece of glassware called a separatory funnel, and upon loading it up with all my distillate, I could now start bathing it in various chemicals. Each one should get rid of different kinds of impurities, and I decided to first wash my benzene with some concentrated sulfuric acid. Upon touching the benzene, it immediately became really tarry. Its addition also generated a bunch of heat, and if I were to do this again, I would definitely use some dilute acid. After shaking the funnel, the whole mixture got so dark it was nearly impossible to see the layers, and I had a really hard time draining off the acid. To try and make the benzene a little more transparent, I washed it with some distilled water, which seemed to really do the trick. I then washed it with a dilute sodium hydroxide solution, then again with some distilled water, and finally with some brine to dry it. After draining off my washed benzene, it honestly looked worse than before, however, on a chemical level, it was much purer and virtually water-free. The final thing I need to do to purify it is, you guessed it, fractional distillation. To make up for all the struggle, this distillation was just textbook, with some beautiful, clear benzene coming over at nearly exactly its boiling point. There was also quite a bit of it which was beyond cool, and when the inside of the boiling flask got too tarry for my liking, I stopped the heating and recovered my product. After so much struggle, I was finally left with this small but not too tiny amount of some carcinogenic water bottle juice, aka pure benzene. I managed to make 38 grams of it, corresponding to a 23% yield from the starting plastic, which is just plain trash, but working on such a huge scale really paid off, since this much benzene is more than enough for some cool experiments. For the first one, I wanted to do a burn test, since being an unsaturated hydrocarbon, benzene should have quite a unique flame to it. Indeed, upon lighting a small amount of it on fire, it burned surprisingly brightly and produced a stupendous amount of this black soot, which nicely coated the inside of my fume hood and will probably remind me of this project for a long time. For the second experiment, I decided to showcase benzene's interesting reactivity, since even though it has all these double bonds, it's surprisingly inert. That's because these bonds constantly alternate and basically evenly distribute across the whole molecule, making it incredibly stable. This is why things like concentrated sulfuric acid don't do anything to it. I mean, it doesn't even go yellow, which also proves that I did a good job purifying it. Nonetheless, some things can react with benzene, substituting its hydrogen atoms for something else, and one of such things is something called a nitrating mix made by combining sulfuric acid with concentrated nitric acid. This mixture is incredibly violent and adds this nitro group onto benzene, making nitrobenzene, which is really toxic and for some reason smells like almonds. Anyway, this project was a really cool one, being really tedious but rewarding in the end, and I think that all this trial and error along with some interesting discoveries were well worth the effort. This method of making benzene, while definitely not as good as some others, proved to be quite reliable, and considering the cost of starting materials, I think it can be great in places where benzene is hard to get. If enough of you are interested, in the future I could try refining the whole process further. However, for now, I want to thank you all very much for watching, since this whole project would not have been possible without you. If you'd like to support what I do, please consider subscribing, liking the video and sharing it with a friend if you want to directly contribute to improving my videos as well as having access to a lot of ad-free exclusive content like my lab tour. I invite you to become a patron. My patrons provide the funds as well as motivation for me to keep creating content and help me improve my videos, and I want to dearly thank each and every one of them for their generous support. Again, big thanks for watching and see you all in the next video.